All right, so then for chapter 11, what we're going to talk about is this idea of fluid statics, right? So this is kind of a bit of a new topic. It's not going to be super related to anything else that we've done before. We'll still have some of the same principles in mind, but we are going to be dealing with these objects now that are fluids, right? So what do we mean by fluid? That's kind of the first thing we want to talk about. For our purposes, a fluid is anything that is a gas or a liquid. Any gas, so just like the air that's around you, we're going to count that as a fluid. Water, any other liquid material, we're also going to count that as a fluid, right? So anything that's basically not solid, right? So far we've been dealing with for the first 10 chapters with our solid objects. We're going to see how they move around and whatnot. Um, Now in chapter 11 and 12, we're going to deal with these fluids, these kind of more malleable objects, right? So we're still going to have some of the same ideas. We're still going to have forces that push and pull on these things, but we're going to see it kind of changes how we need to talk about them a little bit because we can't just have our same equations of motion to talk about, how these fluids move around, right? But again, we'll still have some of the same principles that kind of govern what's going on. We do also need to talk a little bit more about some different quantities that we haven't discussed before. So we have this idea of density, right? So the density of a fluid is going to be very important. So what do we mean by the density? The density of a fluid is defined as the mass per volume, right? So then the units would be kilograms per meter cubed, right? So the density of an object, right? So the density of some fluid is, it's a measurement of how dense it is, of course, right? So, but it's mass per volume. So if you have a lot of mass in a very small area, right, in a very small volume, right, in a very small space, then it's very dense, right? So we're not talking about, we don't know how much it actually weighs, right? The density doesn't tell you that. But if you have something with a high density, a small amount of it, right, a small volume of that, will still have a pretty high mass, right? Or you can have low density, right, where you have maybe you have a very large volume, right? And maybe you have a very large volume of air or something like that. The density is not very high. And so even though you have a very large volume of this fluid, you still have a low mass per volume, right? So it's again, this density is kind of a property of the fluid. You can have more of some sort of fluid, you can have less of it, but the density doesn't change, right? No matter how much water you have, right? The density of water is just whatever the density of water is, right? There are some things that can kind of change it, when we talk in like temperatures and all this pressures and stuff. We're not going to deal with that too much. We're not going to deal with density changing in any sort of dynamic way. We're just going to assume that the density remains constant. That'll be a pretty good assumption for the conditions that we are working under. So yeah, so we have density. It is the mass per unit volume, right? Is kind of what we're measuring with that. So we're going to see the density of these fluids is very important to kind of figuring out what is going on. In addition to that, we also have pressure, right? The pressure exerted within a fluid, right? So the pressure is going to be the force per area, right? So the pressure on any surface or on any sort of object is the force that it is experiencing divided by the area that that force is being spread over. So in this, of course, we have newtons per meters squared would be our units for that, our standard units. There's a couple different units that get tossed around for pressure. I'll try and probably just keep it in our standard newtons per meter squared units. There's a whole lot of different units for measuring pressure. A lot of people have done it in different ways. We're usually just going to stick with our newtons per meter squared though. But yeah, so again with these pressures, right, it's kind of analogous to this density. It's kind of, instead of having our mass spread over a volume, for these pressures we have a force that is being spread out over an area. So you've kind of, again, you've experienced this kind of stuff, right? So you go to the doctor and you have to get a shot or something like that. It might still hurt a little bit, but you have a very high pressure. They're not pressing very hard, but the small force of the sorry about that. Okay, the small force of the needle is being applied over a very, very tiny area, right? And so you have a still relatively high pressure. It'll hurt a little bit. It kind of breaks your skin a little bit as well. Of course, it has to in order to actually, put whatever is going to be in there, right? So yeah, of course, if someone just pushes on you with their hand, maybe they push with a much higher force, but obviously the area of your hand is much bigger than the area of the tip of a needle, so the pressure would be less, right? You don't have to worry about it hurting as much in that case, right? So yeah, so we have this density and this pressure, and this is going to be very important when we're discussing this idea of fluids, right? So in particular, the first thing we're going to talk about is when we submerge something in a fluid, right? It's going to experience some sort of pressure, right? So again, if I have If I have some sort of container here, maybe like a glass of water, and say I put something in it, here's my fluid. Now I put some sort of object in it, right? This fluid that's all around it is going to be applying a pressure from all different directions, right? So it's going to be kind of squeezing this object in like this, right? So there's going to be some sort of pressure that this object feels as it is submerged in this fluid, right? So there's going to be forces kind of squeezing it inward applied over the area of whatever the object is. And so what we're going to try and figure out is the first thing we want to do is figure out what is this pressure experience. Well, first of all, where does this pressure exactly come from? Well, a simple way you can think of it is this, right? This object is submerged in some sort of fluid. The fluid has a mass, right? So it has a weight. There is a gravity pulling the fluid down. Object is underneath the fluid, right? It's underneath some amount of fluid. And so what we're going to have is the weight of that fluid is kind of pressing down. And now, of course, I have these drawn. We did say it's squeezing in on all directions. That is correct. The way it works out is um, we do have the pressure is caused by the fact that this fluid has weight. But when we see how this fluid is going to get pressure on, right, this kind of fluid is pressing down on the bottom, which kind of squeezes this stuff back up a little bit. So it is kind of pushing inward in all directions on whatever object we have inside this fluid. But the way that we can calculate this, though, the way that we can calculate this pressure is still going to be pretty familiar to us, right? So the pressure, as we said, it's the force per area. So the pressure that this object experiences in this fluid is then going to be what? It's going to be m times g, where we have the mass of however much fluid is above it times gravity, right? So the pressure is still going to be based upon just the weight of the fluid above this object. And then we're going to divide it by the area of the object, right? So we don't know what the area of this object is. And what we're going to try and do is we're going to derive, in general, a result for the pressure that this object experiences, whatever this object might be. We don't want to have it depend upon the shape of the object. We want to be able to put any object we want in this fluid and see what pressure is on it. Well, let's see how we can rearrange this. So of course we can write it like this, right? We can say that the mass of the fluid above this object is also equal to rho times v. Rho is our density, right? So rho is what we use, is the Greek letter that we use for density. It looks like a P. You can see I'm drawing it slightly differently though. But yeah, so rho is what we have. The RHO is the Greek letter. Rho times volume gives us the mass of the fluid that is above this, right? Okay, so we have that. So we can also write our volume a little bit differently though, right? We can say that the volume is going to be what? The volume of this fluid is going to be, that's above our object, it's going to be the area of our object times the height, the distance that the object is beneath the surface. So if we are, you know, 1 meter below the surface of our fluid, right, and we have, say, I don't know, half a square meter worth of area or whatever, you can multiply that height, right, by that area above the object itself, and you can get the total volume of fluid that is above this object and pressing down on it, right? So with this, we can actually rearrange our formula here for the pressure, and we can write it like this. We can say our pressure that our object experiences is going to be this. It's going to be m times g divided by a, but now we can rewrite our m, which is going to be rho times a times h, right? And then this is times g, and then we divide this by a, and this is what we end up with. The area will cancel out, and we can write our pressure as rho times g times h, right? So this right away might look familiar, right? Instead of what does it look like, right? We have rho times g times h. This is a pressure, right? So this is a force per volume, right? But what this kind of looks similar to, and we'll kind of see why this is important in chapter 12. This is analogous to, right, our MGH, right? But our MGH seemed like it meant something completely different. So how are they related? We're going to see exactly how they're related in chapter 12. But for now, just kind of remember, we have rho GH gives us the pressure that our object experiences being submerged a height h beneath the surface of this fluid, right? So rho is the density of the fluid, g is the gravitational constant, right? So whatever planet you're on, if you have stronger gravity, you'll end up with more pressure. It's kind of squeezing that stuff down more. And then the further below the surface of the fluid you go, then the further beneath, sorry, the more stuff is above you pressing down on you, right? So a bigger H in this case will give us more pressure as well. So we have rho GH is going to, in general, tell us what the pressure is at a certain depth within a certain fluid on a certain planet, right? So how can we kind of relate this to terms that we're used to? So obviously, we've said that fluids count as either liquids or gases, right? We are sitting here in a room full of air, right? You know, when you go outside, you are in the atmosphere, right? You have air all around you. Air does count as a fluid. Um, and so this air is actually putting a pressure on you, right? And so you're submerged in underneath the surface of the Earth's atmosphere, however far out that extends. Um, so there is a pressure that you experience, and it seems like at first it might be a lot, right? So we have 1 atmosphere. We can call that, just the pressure of the atmosphere at roughly at sea level um, is actually equal to 101,000 newtons per meter squared, right? And so this is actually quite a bit. So the reason why this number seems very high, but obviously you're not getting crushed under the weight of the atmosphere, right? There is the pressure from the atmosphere, right? But this pressure is also, you have the internal pressure inside your body, right? Which of course, as you breathe, right, you're kind of changing that a little bit. But you also have this kind of pressure exerting in every direction, right? So you're not getting squished preferentially in one direction or another, right? And you also, again, you have internal pressure within your body that's also pushing outward with this same amount of pressure, right? So it all comes from this fluid stuff being more malleable, right? You have stuff that's weighing down on you, that's squishing you, but you also have stuff that's kind of pushing out and trying to counteract that, right? Um, so of course, where you can kind of really play around with this idea of varying pressures is, if you take a water bottle, right, an empty water bottle, right, and it's just sitting there fine, it still has the same amount of pressure on it, right? It still has this enormous pressure on it, but it also has the same pressure inside the water bottle, right? But if you suck out all of the air from the water bottle, what happens to it? Well, then it kind of collapses down, right? You're decreasing the pressure inside the water bottle. The pressure on the outside is staying the same, and so you will kind of, as you suck the air out of the water bottle, it will be collapsed down into a much smaller space, right? So yeah, so we do have this is what 1 atmosphere pressure is. This is basically what the pressure is at due to the atmosphere at sea level, right? So just for fun, we can look at if you work out the numbers to it. If you go about 10.3 meters below the surface of some body of water, you will have doubled the pressure on you, right? You still have the atmospheric pressure on you, equals one atmosphere of pressure, right? So by standing at sea level, you have about 101,000 newtons per square meter pressing down on you from the just from the pressure of the air that's above you. If you go at 10.3 meters, right, and so the atmosphere extends up, several hundred miles. But if you go 10.3 meters below the surface of water, right, so this is about 30, 40 feet down, then you will have 202,000 newtons, right? So you'll have doubled that, right? So 10.3 meters below the surface of water is equivalent to being several hundred miles below the surface of the atmosphere. So just to kind of give you an idea for how these densities can vary, right? So of course this is because water is much denser than air is essentially what's going on there, right? If you're 100 miles below the surface of the atmosphere, you get the same pressure as if you were 10.3 meters just below the surface of water. So yeah, so we can derive in general this kind of pressure at a depth, right? We just have by simply being submerged in some fluid, whether that's water or air or whatever other gas or liquid it happens to be, there will be some sort of pressure exerted on that object depending upon how far down that object is. And again, it only matters how deep you go, right? It matters what the liquid is, what the fluid is, right? What the density of the fluid is, what planet you're on, and how far below it you go. So it doesn't actually matter how like wide or narrow this body of water or this kind of container of gas that you're in, right? So if you go 10.3 meters below the water, out in the middle of the ocean, where the only thing that matters is again the water that's actually directly above you, that kind of governs this pressure that you experience, right? Whereas if you go 10.3 meters below the surface of a swimming pool, right? You probably don't have access to a pool if that's that deep. But if you did and you went that far down, um, even though it feels like, out in the middle of the ocean, there's like more water above you, it only matters for the stuff that's directly above you, right? So as long as you go the same distance down, the pressure will be the same, regardless of the what the actual volume of like the container that you're in or whatever, right? So if you were to make just to kind of drive the point home, if you had like a rain gauge or whatever that was 10.3 meters long and you filled it all the way up, the pressure at the bottom of that would be the same as the pressure, 10.3 meters down below the surface of the ocean. The only thing that matters is, how far down beneath the surface do you go? And then, of course, what exactly is the fluid and what planet are you on? But for our cases, we're assuming we're usually underneath water or air. And we are on Earth is a pretty safe assumption. Okay, so we have a couple more principles that we can derive for this fluid static stuff, dealing with, again, just our fluids and our pressures and whatnot that we're going to exert. So the next thing that we can talk about that kind of uses some of these ideas is Pascal's principle. And so Pascal's principle, I'm just going to restate it here. It's in the book as well. Again, we're in chapter 11. I'll just restate it. So what we're going to say is this: a change in pressure applied to an enclosed fluid. So like just fluid in some sort of container, right? So if you have like air in a balloon or something like that is a good example, right? Change in pressure applied to an enclosed fluid is transmitted to all portions of the fluid and its walls. So this kind of seems simple at first, but it has some very interesting implications. So again, what we're saying is if I have an enclosed fluid, again, like just air in a balloon or something like that, right? So it's enclosed in some sort of container. Change in pressure applied to an enclosed fluid is transmitted to all portions of the fluid and its walls. So simply, you can think about it this way. So you take a balloon and then you kind of squeeze it at one end, right? You grab that balloon and you squeeze it really tight at one end, like kind of like you're trying to pop it, but you don't actually succeed in popping it. What happens? What you'll see is that it kind of bulges out at the other side, right? You're applying a pressure, you're applying a force over some area with your hand by squeezing one end of it, but you'll see that pressure then gets applied all throughout the entire area of the balloon, right? It kind of squeezes out, it kind of bulges out. You kind of have this this asymmetric bulge, on the other side of your balloon, right? So in that case, you're applying that, you change the pressure on one end and then you're applying it to the rest of the air in the balloon, plus obviously then all of the walls of the container, which in this case would just be, the balloon itself, right? So the balloon itself then feels more pressure from the particles of air that are now bumping up against it inside the balloon, right? So again, seems rather simple, seems rather intuitive, but there's some neat tricks you can do with it that we can talk about when we get into the idea of hydraulic systems, or exactly how hydraulic systems work. So this is kind of, when we're talking about hydraulics, this is how, this is kind of just a very basic idea of how that stuff works. So let's say that we have a setup that looks something like this. So we have two kind of containers, but they're kind of connected by some sort of like pipe or tubing or something, right? So this whole thing is filled with fluid, right? We have some sort of fluid in here, and we have some sort of fluid, the same fluid in here, right? So we have this fluid that runs through here. So we have one, and these two things that I have drawn here, these are pistons that we can kind of press up and down, right? So if I push this piston down, right, I am applying a pressure to the fluid that is in this container, right? So I'm going to apply a force. We'll call it force 1. This piston has some sort of area area 1, and so I will be applying a pressure to this fluid here. Now, what I have to do as I apply that pressure, I have to apply the same pressure all throughout the rest of this fluid. So what's going to happen to this piston, which is also, again, it's containing this fluid, but it's free to move up and down, right? So this piston is then going to experience a force up, right, as some F2 and A2, right? Um, so this is essentially a very basic schematic for how hydraulics work, right? So I'm applying a force here, which applies some sort of pressure on this fluid. So I push this down, this piston then goes up. But what, how are these forces related? Let's say, I'm just a person, I'm not very strong, right? So I apply some sort of weak force here, but I have an enormous piston on this end here, right? With this A2 is much bigger than this A1. How strong is this force that I get out of it? Well, let's see. So we know that the pressures have to be equal, right? So we can say P1 has to equal P2. Well, what is P1? It's F1 over A1. This has to be equal to F2 over A2. So let's say the area of this piston, right, is 10 times bigger than the area of this piston, right? Then what does that imply for the force that I'm getting out on this end here? If I apply a 10 Newton force from F1, my F2 is going to be what? My F2 is going to be A2 over A1 times F1. But if this area is 10 times bigger than this, then this is really weird, right? I'm applying a 10 Newton force here, but I will get a 100 Newton force pressing up on this piston. That seems like I'm cheating. This seems like I'm breaking some conservation laws, right? But this is how it works, right? And so like when you're trying to, this is kind of used, if you're trying to like lift a car up, right, in some sort of auto shop or something like that, you can apply a small force on this end, right, on one piston, right, a small force on a small piston, and you can get a big force on a big piston. You can kind of, probably don't do it by hand anymore, but you yourself could apply some sort of force that then starts to lift a car off the ground, even though you normally wouldn't be able to. Like as I said before, this feels like we're cheating, right? This feels like we must be breaking some sort of conservation law, right? If I input a 10 Newton force, how can I get out a 100 or even a 1,000 Newton force, kind of depending upon the exact setup. So again, this is why Pascal's principle is so useful. You can apply a very weak force and you can get an output, right? Just like a kind of a little simple machine that we have here. You can get an output of a very, very strong force. So the way this works is you have to keep track of the work being done, right? So for the most part, when I ask these problems for you in this chapter, we're just going to say, okay, here's my input force, what's my output force, and so on and so forth. But if you actually look at the work being done, the work being done here is the same as the work being done here. How does that work? Well, we have to think of it this way, right? If I push this cylinder down, say 10 centimeters, right? If it, decreases from here all the way down to here or something like that, and it goes down a distance of 10 centimeters, I might be able to get a force that's 10 times stronger here, but it will only raise up 1 centimeter, right? And so that's okay, but that is kind of, but it still does give us this advantage, right? It lets us, we can use a weak force applied over a large distance, and we can get a stronger force applied over a shorter distance. But you can still see situations where this would be useful. So the total work done is still the same, right? If you look at the work equals force times displacement, right? You'll have a higher force here, but you'll have a smaller displacement. But yeah, so again, this is just kind of a consequence of this idea of Pascal's principle, right? This pressure here, whatever pressure gets applied here, has to be the same as the pressure that gets applied here. So if we're applying that same pressure over a much larger area, that means we are getting a much larger force, right? We necessarily have to be doing that. So again, this is just a very useful kind of little simple machine that we can make. This is again, this is a very basic schematics for a hydraulic system, which you probably heard the term of before, but this is kind of how it works, right? You apply a small force. This is like some braking systems in cars work like this, right? You press your foot on the brake, and then obviously, you're not strong enough to bring the car to a stop, but it kind of you can clamp some brakes that are strong enough, right? They don't the brakes themselves don't have to move very far to clamp on the wheels of the car. So yeah, so you slam on your brakes and then you apply a much stronger force on the wheels of the car to actually help slow the car down is another example. But yeah, so weak input force and strong output force all from this very simple Pascal's principle. Okay, there's one more concept that we'll discuss then for chapter 11. So the last thing that we're going to talk about is Archimedes' principle. And so what this is going to say is this deals with the buoyant force. So talking about why objects seem to float in fluids. So we're going to have the buoyant force. So we have the buoyant force is the net upward force on any object in any fluid. So what we're saying is if I submerge an object in a fluid, we always you will always notice that that fluid overall is pushing that object up, right? It will apply a force up. Gravity might still be pulling it down. Gravity might be winning, but there is a force applied by the fluid that's trying to push that object up. Well, again, let's go back to the very first thing we drew, right? I'll draw a little bit better this time. So we have some sort of beaker of fluid. Looks like this, right? So here's the surface of my fluid. And then we submerge some sort of object, some sort of little cylindrical object inside of it, right? So this object is now submerged in the fluid. As I said before, it experiences a pressure based upon the depth of that fluid, right? Or sorry, based upon the depth of the object beneath the fluid is what I should say. So we have some sort of pressure pushing down here. We have pressures pushing like this. And then we have some sort of pressure pushing in this direction, right? And so of course we have some sort of area for the cylinder, at the top of the cylinder, so we can calculate exactly the force. But why then, is this always being pushed up? Why is the buoyant force always going to be up, right? You never put an object in fluid and then the fluid acts to sink it all the way down, right? Gravity might act to sink it all the way down. That's something different. But the fluid itself will always push this object up, right? It will always oppose the direction of gravity. Why is that? Well, as we said before, right? This pressure is based upon what? So the pressure at the top here, we're going to say that this is P1, we're going to say this is P2. These pressures on the left and on the right are actually all going to cancel out, right? They're not going to contribute to the net force experienced by this object from the fluid. However, P1 at the top is equal to what? We have rho times G times H1, whereas P2 at the bottom is rho times G times H2. And essentially what we're saying is this: any sort of three-dimensional object, which of course, if you're submerging it in the fluid, it's probably three-dimensional, is going to experience a buoyant force upward because the bottom of the object is simply lower in the fluid than the top of the object, right? It's has been submerged further. So the pressure on the bottom of it, right? This pressure is squeezing in from all directions, right? It's just kind of a result of, again, all the little particles and atoms of the fluid kind of bouncing around and colliding up against it. They're only going to hit it, right? They can't like attach and then drag it down or anything there. They can't like grab it and pull it down. So they are only going to push into it, right? They have to bounce off of it into it, right? So they have to be pushing, squeezing this object in towards itself. But the ones that are on the bottom are at a lower depth in the fluid, right? And so, of course, as it turns out, they are then, this is going to be a higher pressure on the bottom, and so you will always experience an upward force from the fluid itself. Now, this doesn't necessarily mean that every object floats in every fluid. Of course, you don't. Right? If you toss a rock in the water, right, the rock will not float. The water will be trying to push the rock up, but gravity will win and will overcome the buoyant force and will pull it down. And so the way that this works is this: the buoyant force itself that this object experiences is equal to the weight of the displaced fluid, right? So essentially, this object here has some sort of volume. So it is this volume. So if we put like our little cylinder inside water, right? It's displacing some of the water, right? This space would otherwise be filled with water. Now this space is filled with whatever this little block of stuff that I've put in this fluid is. And so it has displaced a certain volume of water, however much that volume of water weighs, right? Whatever the actual gravitational force on that water is, the weight of that water that is displayed, that is going to be equal to the buoyant force. And so this is why objects that are less dense than the fluid float and objects that are more dense than the fluid sink, right? If this is more dense than water, right, it's taking up the same volume as the water that would be there. So if it's more dense, then obviously its weight is more than the weight of that water, right? So the buoyant force, right? So we have the buoyant force is going to be pulling up, then we have the mg of the actual object pulling down. So if this object is denser than water, right, this is equal to the weight of the fluid that it displaces, right? So the gravity pulling it down will be stronger than the buoyant force pushing it up, right? If it's less dense, obviously, then the force of gravity on this object will be less than the buoyant force, right? So the buoyant force is, again, just dependent upon the weight of the displaced fluid, right? And so this is how you can tell if your object is going to float or not, right? Calculate this volume of the object, and calculate the weight of the water or whatever other fluid you are displacing, right? So you standing in the atmosphere, you actually do experience a buoyant force from the air that's around you. But of course, the volume of air that you displace doesn't weigh that much, so it's a pretty weak buoyant force. But of course, if you fill your balloon up with helium, helium is less dense than the air. Now it's displacing air that is it's displacing air that would weigh more than it, so the buoyant force upward is enough to actually push that helium balloon all the way up. So these are just kind of the basic principles that we have for our fluid statics, right? We have our pressure at a depth, we have our Pascal's principle, and we have our Archimedes principle, right? So after this, we'll get into chapter 12, and we will discuss fluid statics, where we'll have some of this stuff actually moving around. We'll kind of see how that relates to this stuff here.